All right. Good morning, everyone. Welcome to the 2015 Legion Bootcamp, second one we've done. I appreciate everybody coming. We have 2 sessions this morning, and then lunch, and then a couple of sessions in the afternoon. And I'm just going to start out with an overview of what has been going on in the project. And since there are some people who haven't been here before, I thought I would start by just saying a little bit about Legion. And what it is, and this will be boring for some people who have seen this sort of thing in the past, but then I'll move quickly into talking about what we've been doing in the last year. So first, a little bit about logistics. So I guess everybody figured out how to park, and we have lunch is in the other room. All the food is going to be in the other room, and there should be coffee and things there all day. So if you want to step out to get a drink, that's completely fine. And there's dinner tonight. Everybody should know about that. If anybody doesn't, then please talk to me in one of the breaks, and we'll get Sue to figure out if we can fit you in, if anybody wants to come, who isn't already signed up. And then tomorrow is our programming exercise. So we're actually going to do some Legion programming, and so bring your laptops for tomorrow. All right. So the focus is going to be on the user point of view of Legion. So we'll talk less about the internals, although there'll be quite a bit of that actually. But we're going to focus more on what people need to know who want to actually be users. And what I'm going to do is we're going to give you a brief overview of the programming model, and then we'll have all the talks are going to be on the major changes that we had in the last year. We'll have a talk this afternoon on a port of Mini Arrow. And some work that we've been doing with that application, because many of you are familiar with it, and so it'll be a good deeper dive into how you tune a Legion program and the kinds of issues that might come up in writing a program that you want to run at scale. And we'll also talk some about debugging and profiling. So a little bit of boilerplate. I mean, just kind of the philosophy behind the project. So. Our goals are to be high performance, to provide performance portability, meaning it should be easy to move these programs from machine to machine, and especially between machines that are quite different from each other. Maybe they have accelerators, maybe they don't. And to provide programmability. So something where it's easy to understand whether you're getting the right answer or not, and a decent software engineering structure so that you can scale up and write large programs where the subsystems compose nicely. And actually, there's a lot of debate right now about what the future of exascale kinds of programming is going to look like. And the truth is, we can actually do this already today. All right, but it's really hard. And to give an idea of why it's hard, here's the task graph for one time step on one node. So this is a Legion task graph. And not every programming system, actually most programming systems don't have an explicit task graph, but if you are the programmer and you're writing one of these programs, you need to have in your mind, what the order, what the ordering dependencies are on the various things you're going to compute. And so at least there's a task graph in your head, even if it's not made explicit in the programming system. And this task graph is for one time step of one node of a mini app. All right, so this is a really simple task graph. And the problems that you come across in any programming system, and it's not just Legion, but any programming system for high performance machines, somebody has to decide how to schedule this graph. And again, the graph may be implicit, but the code that you write will imply certain ordering dependencies and have synchronization in it that will essentially amount to a scheduling of this graph. When you move it to a new machine, and this has been our experience, when we move from one machine to another, or if we even change the input characteristics, say a different kind of workload of a particular program on the same machine, we often want to reschedule the graph. So the graph very frequently needs to change in order to get good performance, either because the input changed or because the underlying machine changed. And then finally, where does this graph come from? So who is creating this graph and figuring out what all these dependencies are between the various pieces? Is that the programmer, or is there some programming system help from that? And today, I think it's fair to say that this is all the programmer's responsibility, okay, in the programming systems that we have. And what we're trying to do is come up with a system in which more of this is the programming system's responsibility, so that a lot more is done automatically and calculated for you, rather than you having to do absolutely every little thing yourself, when you write one of these codes or move it to a new machine. All right, so what's Legion then? It's a programming model for heterogeneous distributed machines, by which we mean machines that have different kinds of processors and various kinds of memory, and particularly a lot of variability, so that not everything performs at the same speed, and both the memory and the processor infrastructure is going to give you some fast things and some slow things. We're trying to design something that's a real programming system. Admittedly, we're an academic group. And so that gives us a certain personality that you wouldn't find in other kinds of groups. But we really try to make this a practical system with good abstractions and semantics that you can actually understand what it's supposed to do. But also it's unusual in the sense that we provide ways to drop down and to take off some of the constraints that the programming system provides and to program at a lower level if you want to, still within the model, but to allow you to take more control if that's what you want to do. And I'll actually talk more about that today. We haven't talked about that much in the past, but I'll go into some detail on that in this talk, actually. All right, so what is actually in Legion? So we have tasks and regions. A task is a function, that's the unit of parallel execution. And tasks work on regions, which are just collections. And these collections have rows and columns. And the rows are an index space, so that's just like an array has an index space. Regions also have some kind of indexing scheme, so you can get to the various rows. And then you can have one or more columns, which we call fields. And so there's just an extremely simple region, which is a vector of floats. And that would be the input, to, one of the inputs to this particular task. And one of the things about Legion is that the tasks have to declare how they're going to use their regions. So for Saxby, we have two regions, okay, which are both vectors. How do you know they're a vector? Well, because the index space that these regions take is a 1D index space. And of course, then there's the constant that you're going to multiply by. And what is this task going to do? It's going to read the x and y regions, so it's going to read both vectors, and it's going to write to the y vector. Okay? And if I show you a little bit more about what it looks like, here is how you would write such a task in Legion. So the declaration up there at the top, the prototype is exactly the same, and then the body is exactly what you would expect. Okay? All right, so that's the basic idea. Okay, so you have tasks, they take regions, and regions are these things that have index spaces and fields. Now, one of the things that's absolutely crucial in Legion is the partitioning system. So built into the language is the ability to partition regions into subregions. And this is a primitive operation and designed to support describing arbitrary subsets of a region. So you can break up regions any way you want into subsets. And just as another example, this is one that you'll be seeing a lot because it happens to be your programming exercise for tomorrow, so it's a good time to pay close attention, all right? We're going to be looking at an electric circuit, which is just a graph. So here the nodes are where the wires connect and the edges are the wires. And let's say we want to partition that we have one big region, which is the entire set of nodes, let's say, of the graph, just the nodes, not the wires. But we want to break it into 3 pieces. Okay? So conceptually, the way that's going to work is that you're going to first partition this graph into 2 subsets. And this might not be what you would first expect. Some of you have seen this example before, but if you haven't, this might be a little bit of a surprise. The initial partition is going to be into the red things and the blue things. Okay? And the red things have the property that they're on the boundary of one of these pieces that we eventually want to create. Okay? So all the red things live on the border. And then the blue things are the things that are completely internal. The blue nodes are the ones that are completely internal to one of the 3 pieces. And we draw pictures like this. If you have the set of all nodes, then we're going to partition them into the private nodes, the blue ones, and the shared nodes, the red ones. And then what we're going to do is subsequently partition the private nodes into the 3 pieces. Okay, and I'm just showing one of the sub-pieces there. Say P1 here is the subregion of all the private nodes that's just in that first piece. And then there are 2 other sets of private nodes for the 2 other pieces. And we'll partition the shared nodes similarly into the 3 subsets for the 3 different pieces. And then finally, the ghost regions, these are the ones that are on the boundary of a piece but are on a different piece. So for this piece up here in the upper left-hand corner, the green nodes here are the ones in its ghost region. Okay, so these are the pieces on the boundary of on the boundary of this piece, of piece 1, but in another piece. All right? And the interesting thing about the ghost regions is 2 things that are interesting. First, they are a different view onto the same data. So we have the set of shared nodes, okay, and every piece has its own set of nodes that are internal to it that are on the boundary, and then a set of nodes that are on the boundary but in another piece. Okay, so the ghost sets, the ghost nodes, and the shared nodes are exactly the same set, okay, of nodes, just divided up differently. All right, so that's important and captured by this region tree structure. And the second thing is that the ghost nodes actually can overlap. So if you look here, this node in particular is on the boundary of multiple pieces, and so will be in the ghosts set of more than one piece. All right, so these other partitions are disjoint, indicated by the black bar, meaning all the subregions don't overlap. And then this particular partition is aliased, meaning that these particular subregions can, in general, share elements. All right, and so this data structure is something that's very useful for the program, but also crucial to the runtime system. So we actually build these region trees internally inside the Legion implementation, and that allows the system to reason about the structure of the data, whether regions are disjoint from each other or potentially overlapping, or whether they are views of different data sets or onto the same data set. Okay, so a lot of information is extracted from these region trees. All right. Now, so the summary of regions, then, that we have entries, okay, say a bunch of nodes in a graph, and then you have fields, which are the columns, and so in the electric circuit example, there might be a bunch of different properties for each node of the graph. Okay. And then regions can be partitioned by rows, so you can break regions up into subsets based on putting different, in this case, in the graph case, different sets of nodes in different subregions. But you can also, I won't show you an example of this now, but you can also slice them by field. So you might have tasks that only use the voltage and capacitance fields, and other tasks that only use the inductance and charge fields. And so you can also specify that when you write tasks, and that would also help the system detect potential opportunities for parallelism. All right, so now you can break regions up into subregions. You can also break tasks up into subtasks. So, and the idea here is that we're going to provide a sequential semantics, but the system will extract parallelism from the launch of subtasks. And so this is an implicitly parallel system. And the way the system does that is that if the tasks do not interfere, then it will be able to launch them in parallel. And by interfere, I mean that they don't compete for each other in an unfortunate way on the regions that they want to read and write. All right, so here's an example. This is a very artificial example, but will illustrate the idea. We have a task that takes 3 regions, and it's going to read and write both of those, all 3 of those regions. Okay? This is the top level task. And then it's going to call 4 instances of this subtask bar. All right? And here's the prototype for that task. It's going to take 2 regions, R, which is its read set, and S, which is its writes, which is what it's going to write to. Okay? So it's going to input region is R, and the output region is S. All right? And what's going to happen when the runtime system executes this particular program is that it's going to be running along, executing the code, and it's going to be issuing tasks to the underlying Legion runtime. All right, so you can think there's a layer down here, which is the Legion runtime, which is going to accept task launches from the program and do something with them. So it's just going to execute the program sequentially. So it's going to get to this task launch first. And so it will just send that over to the Legion runtime, and the Legion runtime will start working away on that particular task. And then it's going to launch the second task, but it's going to discover that this task is dependent on the first task. Okay, so in particular, because this task is writing y and this task wants to read y, it's going to have to wait for that result before it can run this task. All right? Then it's going to issue the third task, which is going to discover is also dependent on the first task, but not on the second task. Okay, so now there are two tasks that are waiting for this task to finish, and the runtime system will keep track of those dependencies and schedule them when the first task completes. Then it will issue the fourth task, okay, which depends on the previous three. And the important thing here is that this thread, this execution thread up here, is actually running ahead, issuing the tasks, even though the previous tasks have not completed. And so this graph is being built dynamically and also executed dynamically. So the Legion runtime is sending these tasks out to be executed, and in the meantime, it's building more of the graph that we'll use to plan what it's going to do in the future. And that ability to run ahead and build up a bunch of work to do and decide, make all the scheduling decisions before the stuff actually has to execute is one of the key things that the runtime system does to hide all the overhead of the dynamic analysis and to make sure that when tasks are actually ready to run, all the resources are already in place. Okay, so actually, when things are working well in a Legion program, you're using a little bit of resource to build and analyze this graph, but mostly you're just constantly able to keep things busy. As soon as one thing finishes, the next operation is completely ready to go. And that's the way we deal with high latency and variance, is by building up enough additional work that whenever any resource comes free, we can immediately find something else to assign it to keep it busy. And I forgot to say at the beginning that questions are welcome during the talk. I could just drone on, but it'd be better if people ask questions. Yeah.
Quick question regarding the dependency graph. The
Yeah.
tasks here. The dependency, whether it's a read query or write query, doesn't change anything, right? In terms of how the dependency is built. Like for example, bar xy has a dependency on bar yx.
Yeah.
Just because x and y are present, or because one is a read and the other one is a write?
Right, so here there's a dependency for two reasons. One is because you're writing y and then reading y here, and the other because you're reading x here and then writing x here.
Both ways.
Right, both ways. Now it turns out that the write after read dependency you can break, and that's an option in the runtime if you want to break write after read dependencies by making copies of regions. There's enough information because we know what regions are. We can actually break those dependencies if you want. That's an option. Yeah.
You have both the read and the write access?
I'm sorry?
Can you access the same region both in
Yes.
and write?
Yeah. You can simultaneously read and write. Yeah. It's not. You're allowed to do you can do updates in place and side effect regions that you're also reading. So it's not functional in that sense. Okay. So on a particular region, you can have whatever side effects you wish. Yeah.
The task annotation is on bar, so all calls to bar will become subtasks.
I'm sorry.
All the calls to bar become subtasks.
Yes.
Is it possible to make a sequential call to bar, or is it always that bar is considered a task?
Yeah, so bar is a task, and so it will go through the task processing. We do, so the question was, is bar always going to be a subtask? Yeah, so the fact that it's a task will mean it will go through the system, and if it's required to be sequential because of its dependencies, the system will enforce that. You're also free to call other functions that are not tasks that, from tasks, and those just execute on the local processor in the local address space. So you can call out to C and C++ functions that are not tasks. Now, Sean wants to clarify something.
Actually, so marking something as a task means that it can be run as a subtask, and the default is running as a subtask. We're going to talk much about mapping later on, and one of the options the mapper has is to say, no, I want to inline this.
Yeah.
So, as I understand it, it's writing the second argument, right?
That's correct.
So can it get rid of the bar XY call because you're doing a bar ZY later without accessing Y beforehand? So you're writing and then overwriting that value again. So is it smart enough to know that? And also why on that bar ZY is it dependent on all three of those?
Probably because I made a mistake and I was editing this slide late last night, and so there may be an error here. But let's see. So what are we supposed to do? So it's writing. No. So we have a write dependency on y here.
Yeah.
Okay. So now we could break that dependency because this version of y won't be used in the future. But if you only want to keep one copy of the data around, then we have to wait for this to finish before we do that.
But your point that bar x, y there is dead, that code is correct, and we currently don't attempt those optimizations in runtime. It's something we've talked some about,
You're going to pass the mic around? Okay, yeah.
right. So limiting code in the runtime is something we've talked about a little bit. I think the current thinking, though, is that it's the sort of thing where we'd like to give you a warning and suggest that maybe you've got something you should just clean up in your code instead, rather than expecting us to always spend the runtime effort to nuke the code at runtime.
Right. This is an artificial example, too.
But we do have enough information to detect these cases.
All right, so I think the floodgates have opened behind you. Why don't you just leave the mic on, Sean, right behind you to the, yeah.
Hi, so my question is, what if the programmer makes an error where the annotations don't really match the regions that he actually touches inside the task, right? Do you understand?
Well, so in the C++ version of the interface, there's no checking, and so
Okay.
you just get incorrect results. In the language version, level version, which we're going to talk about today, there's static checking of that sort of thing, and you'll get a runtime, you get a compile time error.
There are some checks you can turn on, but they're expensive.
Right.
Okay.
Right. And actually, yeah, so I should say the runtime system also has a bunch of checking, but it is expensive if you want to turn it on. Right. So, okay. I'm going to try to keep plowing ahead here so we don't get behind, but keep asking questions if you want to. So the mapping interface. So far we haven't said anything about where the tasks run or where the regions are actually placed, and that's deliberate. So we try to maintain an interface there, or a level of abstraction that, where at the program level, you don't say anything about exactly where tasks and regions live. Okay, so then it's the job of a mapper to select those, to decide, which processor a task will run on and what memory will hold a particular region. All right, so I have a bunch of tasks. I have some sort of machine, okay, with some processors and some memories. So then the act of mapping is to assign each of those tasks either to CPUs or GPUs in this case, and each of the regions to one of the memories that are going to be accessible to the corresponding tasks. All right? And again, so mapping is a separate operation. It's computed dynamically. It's under application control. So the application can make, if you have domain-specific knowledge about your application, you can make application-specific decisions. And one very important property of the mapper is that it decouples correctness from performance. So any mapping that you choose will be correct. It will give you correct execution. It might be very slow. But then fiddling with the mapping is an optimization. So essentially, you can tune your program by looking at what the program is doing, using the profiling tools, and then trying to improve the mapping. And we'll see some examples today in detail of improving the mapping of an application. All right, so back to the top. Yeah. Yep.
Is mapping only for the placement, or also for the order of things that are, might be more performant in particular situations?
Well, you can't change the order of things with respect to things that are dependent. Okay, so if two things actually have to be in order, then the system will conserve that. But one of the things you can do in mapping is to give priorities. So if you know particular kinds of tasks that are, for example, going to be on the critical path, you can say when you see one of those and you have a choice, we want to schedule that first. And we actually very much use that, for example. So there are ways to affect the scheduling order. And it's more than just placement of tasks and memories. There's a whole lot of other functionality in the mapper if you want to use it. Yeah. Okay. All right. So in Legion, the Legion system is going to schedule the graph in conjunction with a possibly custom mapper. When you move to a new machine, generally all you're going to do is write a new mapper. And we actually have had a lot of success with that. We run on lots and lots of different machines, and typically porting even a very complex application is only a few hours of work. So this is one of the things that we've exploited ourselves in our research when we've needed to switch machines, and we do this a lot, actually. And finally, who generates the graph? Well, in this case, the graph is generated by the runtime system. You write what appears to be more or less a sequential program. You have to specify the regions and the subtasks and things like that. But then figuring out all these dependencies, that's done by the runtime system for you. All right. Now, a little, yeah, question in the back.
That might be a great question, but for analysis, can I actually get an explicit representation of the task graph or a piece of the task graph out somehow?
Yes. So the question was, can you actually look at the task graph? And we have, so very much you need to do that sometimes to debug what's going on. And so we have tools for doing that. But the point is that the system is computing it for you and you're inspecting it rather than imagining what it might be, right? So you have a way to, and we'll actually see examples of that today. All right, so besides read and write, the other kind of permission that you can have on a region is to do reductions. So I thought I would get that out there because we will see some examples. And when you have a reduction permission, you have to name the function that you're doing the reduction with. And now I want to add something that we haven't talked much about in the past, although it's always been there, which is coherence. And so you can also say, well, I actually don't care about sequential semantics, okay? Or I would like to relax the sequential semantics. So for example, you can declare that a task will be atomic on a region instead of having to be exclusive. So when you have exclusive coherence, that means you're only, when you're reading that region or writing that region, you want to be the only task. It should appear that you are the only task using that region, okay? And it should observe the sequential semantics of the original program. When you declare atomic coherence on a region, you're saying, when I use this region, I want to appear to be the only one using it, but it's okay to swap me with other tasks that have atomic coherence on this region. You can actually change the order of tasks, even if they're dependent, provided they also are only atomic. And then simultaneous coherence means, actually, it doesn't even have to appear to me that I'm the only one using this region. Okay, it's okay for other tasks to be simultaneously performing updates to this region, and that's okay for my application. All right? Now, what does this actually mean? So coherence is with respect to your sibling tasks. So I think this little example will help explain that. So we have a top-level task here that reads and writes its input region and has exclusive access. Okay, that means that with respect to all the things at its level of the code, so all the tasks that foo runs in parallel with, it will need to observe the sequential semantics. Okay? But inside of foo, it's going to have two subtasks, bar and baz, which only require atomic coherence on the region. And what that means is that even though they are dependent on each other, because they both read and write the input region, the scheduler is going to be allowed to reverse the order of these two, if it wants to. Okay? So within the scope of this particular task, it's okay to reorder these sibling tasks. And so coherence is always with respect to your siblings. All right? So we're just looking at the tasks that are issued by one the subtasks that are issued by a single task. And any kind of relaxation of the coherence will be with respect to the tasks in this task body. And this, as I said, the same thing goes for foo. Whoever is calling foo and all the subtasks it's issuing, foo is saying, I need to appear to be sequential with respect to those sibling tasks. So it's a very hierarchical way of controlling the coherence and allows you to relax it locally so that you can have some hope of understanding what you did and debugging it if you run into problems. Okay? Now, you can also have simultaneous coherence, as I said, and in this case, this would mean that it's okay for bar and baz to actually run in parallel and do updates to the region, and for that to be visible to both tasks, both subtasks. But foo itself is still exclusive. I didn't put the keyword there, but that's the default. Okay, so exclusive is the default coherence if you don't say anything else. So even though bar and baz will be executing simultaneously, potentially, when foo is running, foo itself will be, appear to be sequential with respect to its sibling tasks. Now, why am I telling you about this? Well, because we're going to talk about coherence quite a bit today. And so you have this way to progressively relax coherence if you want to inside of Legion, and to have more and more visible concurrency. And simultaneous coherence in particular implies that the programmer is going to be involved in managing that concurrency because you have uncontrolled writes potentially, between the two tasks to the same data. And so there's additional primitives that go with simultaneous coherence to allow you to manage the order of those writes if you want to. So you can locally have operations we call acquire and release, which will allow you to make copies of the data, okay, to basically make local copies, all right, and which is a dangerous thing if somebody else could be writing to the data, for example, because then you won't see their updates, all right. And we have a lightweight phase barrier, like X10 phasers, that allow you to synchronize between tasks that are accessing data simultaneously. And I'm not going to go into any more detail about these. We'll talk about them a little bit more later. But this is just an example of opening the hood. So this is a way for the programmer to say, OK, I want to take responsibility for the coordination between these tasks. I'm not going to use the generic dependence analysis of the runtime system. I'm going to say, basically, don't do that analysis anymore. Let these things run in parallel, and I will manage the interaction between these tasks myself. But again, it's very local. It's confined to those subtasks. And in the larger scope of things, you can still have the semantics that the larger, say, sequential semantics if you want to rely on that. All right, so this is just one way to kind of drop down a level of abstraction. Yeah.
So, I mean, basically, exactly on that locality point, if you're specifying simultaneous but not with respect to what, how do you know that some other library that you're calling doesn't also request simultaneous with respect to its own stuff, but not with respect to your stuff?
Well, that's fine. I mean, so the system is still doing its analysis, right? So the system still knows the dependencies between various components. So if you have another subtask somewhere else in your computation, some other task in your computation that's working on disjoint data, and there's a bunch of subtasks that are going to simultaneously access that data, it's fine for that to run in parallel with this, okay? And that's managed at some higher level, whatever task originally called those two tasks that led to these different simultaneous computations. Am I answering your question?
I think so. You're saying it's at the exact sibling level, and there's no way
at the sibling level
to do simultaneity off generation.
There's no way to do simultaneity off generation. If you wanted to have that, you have to kind of pull them all up into the same parent task. So you would restructure your program so that they were all being issued at that level to make that explicit. Yeah. All right. So this is how S3D is structured. Okay, and S3D, for those of you who have heard us talk about it before, is a combustion simulation. It's a collaboration that we've had with Jackie Chen's group at Sandia. It's done as part of the Exact Center. And so this is the way we scaled S3D up to many thousands of nodes. So and the strategy at the top level, so we partition the volume across nodes. We launch one long-running task per node, okay? And some of the data that's in regions passed to that task is private, meaning it's going to be used with exclusive coherence and just within that node. But some is shared with other nodes, like the ghost regions that have to be updated on the boundaries between the pieces of the volume. And those we access with simultaneous coherence. Okay? And we use these acquire and release operations to mediate the access to those regions. And then within a node, we launch subtasks that have either exclusive or atomic coherence. We also use the atomic coherence there. All right? And then, of course, some of the tasks are mapped to the GPU and some to the CPU. So this is the way we managed to do this, and we're going to walk through an application later today where we'll explain it has a very similar structure and explain it in more detail. But this is what allows us to scale S3D up, and we've run it on over 8,000 nodes on Titan. And I'm not going to spend much time on this because we're already getting behind. But the performance numbers here are compared to the OpenACC MPI hybrid code. The comparable Legion numbers are quite a bit faster. Okay, and I'll just show you a quick picture. Here's the mapping for the 96 cube points per node for one node on Titan for the heptane chemical mechanism. And I just want to point out a couple things here. First of all, we're using both the CPUs and the GPUs. Okay, this is one core dedicated to doing the analysis, the dependency analysis. This is the Legion runtime up here, doing all its dependency analysis tasks. But the main thing to observe here is the ragged phases. So, this is something where you could program it with MPI and barriers, but notice, that like these purple nodes, these purple tasks here, they don't all end at the same time. And because we support more asynchrony than something with barriers, we're able to take advantage of these ragged fronts to pack in more work. And you'll also see places where some tasks have been interchanged. So here you can see like this purple task sometimes gets done before the green tasks and sometimes after. So things are getting swapped around where things run a little bit slow and we need to find some other piece of work to do. Okay, and this is what allows us to really pack things in and to do a very good job of not having very much white space on any of those. All right. Okay, and then the other thing I would just say about S3D very quickly is that by using the mapping facilities, we were able to do a chemical mechanism that nobody's done before. So we've done the primary reference fuel mechanism with 116 chemical species. And here, the ability to manage the data very well was really crucial. So the ability, because we couldn't even fit this into most machines using standard techniques, but we were able to map things very carefully and get it all to fit and run this at scale. Okay. All right, so the bottom line with Legion is you have these critical design decisions. What are the regions? How are the regions partitioned? And that's how that's what drives the design of your program. All right, now, I want to spend a few minutes talking about the past year. I got about 4 minutes if I'm going to stay on time. And I got 10 slides to go. So let's see what happens. All right, this may raise some more questions. All right, so the project has changed in the last year. So we've grown substantially as a group. We have lots of interaction with users, and we've learned a lot about Legion, including a lot of flaws in the design. All right, and we made a decision about mid-year, thinking about what we were going to do and how we were going to move forward, that we were going to spend some time fixing core issues. So we did find some problems, and we decided to bite the bullet and fix those, even though they involved major changes, because we figured this was not going to get any easier in the future. I mean, as the number of programs written in Legion increases, it's going to be harder and harder to do breaking changes that are not backwards compatible. So we went into a hole for about 6 months, and we're just coming out of that now. And a lot of new features are starting to roll out, and I think because we took the time to really shore up the foundation, we'll be able to make very rapid progress over the next 6 to 12 months. All right, so what are some of the problems? Well, one is that we've heard a lot that the C++ API is verbose and a lot to learn. There's a lot of Legion semantic requirements that aren't checked there, and there's no help with kernel code. So Legion, the C++ API is about the tasks and the regions, but doesn't actually generate, say, particularly good task code for you. So whatever you write in C++ is whatever you get for the task code itself. And so we decided this was something we weren't going to try to address in the C++ API. I mean, one of the reasons that it is a lot to learn is that there's a lot of template stuff in there to allow it to be parameterized for performance in different situations, and just adding on top of that, which would be the only mechanism we would have for addressing some of these things, we decided wasn't the right way to go. So what we've done is we've added a new thing on top of the Legion runtime. So and this is just to show you the Legion runtime is divided into a high-level runtime and something called Realm, which we'll hear about more, as a low-level runtime. That all sits on top of GasNet. And then applications are either just straight-up applications like S3D, or they're domain-specific languages that generate code to the Legion runtime. And we decided to add a real programming language here that implements the Legion model, and Elliot's going to talk about that next. All right. And actually, all the code I've been showing you is Regent code. So this is actually real code that compiles and runs, and this is what it looks like in Regent. All right. Okay, problem number 2 was we found some problems with our partitioning system, which we were very proud of. The problem was that it wasn't so easy to actually parallelize the partitioning itself. And there were some reasons for this, but we're not going to go into them because we're throwing out the old partitioning system and introducing a new one, which we like much better. So we're even more proud of the new one. And it actually solves the problems that people had, and it's much higher performance as a side benefit. Problem number 3 was with the mapping. So Michael explained our mapping interface kind of grew by accretion as we discovered things people wanted to map, and in the end it was all kind of a hodgepodge. And so we have a new mapping interface that he will talk about this morning. Actually, I think it's this afternoon. Maybe no, it was this morning. And then another issue was I/O. So the original Legion implementation didn't deal with external entities at all. It could interoperate with MPI, which is how we got Fortran, how we got S3D to work, because we let the old Fortran code. We kept enough of the old Fortran code that it could do checkpointing and read the file format for us, which is, the I/O piece, and then we did all the computation inside. But that's obviously not a great long-term solution, and so we need to be able to interoperate with external data sources, and so now we have a new I/O subsystem. And then finally, we ran into problems, and I'm saying this mostly to apologize to people in the room, where we would be pushing changes to the repository, and then people would be checking those out and discovering that they couldn't do any work because we had had a bug. And we just had kind of undisciplined software engineering. And so that was actually by design, because we didn't want to have all the overhead of a full software engineering process while we were still a small group and trying to move quickly. But that doesn't work anymore, and so we've taken some time to clean up the repository, to invest in testing tools and infrastructure. And this is all the way from the very mundane things that you would expect in a real software project up to some kind of researchy things that we're doing. But this has gotten much better over the last few months, and now I think we're in a point where you can sort of expect that the current stable version, when you check it out, it will be stable. We have a process for pushing changes to it that will only get there when things have been relatively well tested. And so this should no longer be a big issue. All right, so I told you a little bit about what we're doing. We're going to have talks on each of those topics that I just went through. So Regent, partitioning, mapping, I/O, and debugging and profiling tools. And then later in the day, we'll do an application walkthrough. Wan Chan's going to take us through his experience scaling up Mini Arrow. And then we'll also have some people who have been using the system talk a little bit about their experiences. And I should say these are not the only things that we're doing. We have a whole bunch of other changes and features coming. Those aren't, but we're not going to talk about them so much, and I'll just go over that quickly at the end of the day when everybody's tired and not paying attention. Okay, so I think we're right on time. Elliot, why don't you come on up? We're not quite on time, so we can take a question while we switch over. Yeah. Yeah, so that was one of the things we're not going to talk about today that I was going to gloss over at the end. And the answer is yes. So it's a well-kept secret, but I am writing a manual, okay? And I have about 50 pages of material done. And unfortunately, I was teaching this quarter, so I didn't get to work on it. But next quarter, I'm not. And come hell or high water, I'm going to get that out the door before spring quarter when I'm teaching again. So yeah, no, I mean the lack of a manual and any kind of documentation other than reading code examples or calling up Mike or Sean, this is a bit of an issue. I agree. Yeah.